So over the last few years, we've been trusting AI and machine learning models with increasingly important and risky real-world tasks, moving from things like movie recommendations towards self-driving cars. And we can't really explain how these models work or when they might fail. It's a big problem. A lot of people are working on it, but I'm focused on wavelet-based neural networks. So wavelet-based neural networks are a little different from traditional neural networks, where we have a training process where we update the models in the parameter based on our data. In wavelet-based neural networks, we preset all of those parameters using wavelets. This was inspired by noticing that the parameters the models learn tend to look like wavelets anyways. So if we just start with wavelets, we can control a lot more about what kind of features the model extracts and prove things about them mathematically that can be pretty useful. So the most famous example is the scattering transform, which is provably invariant to translations and stable to small deformations. So we have two pictures of a 6, and if we compare them pixel by pixel, they're very different. But if we pass them through the scattering transform, thanks to this mathematical theory, we're guaranteed to get two outputs that are pretty close to each other. So why should we care about mathematical theory in practice? Well, traditional neural networks have been shown to be quite sensitive to small changes in the input. So you can take a picture of a pig, you can add a tiny amount of noise, it's imperceptible in the changed image, but it can cause the model to make a pretty significant mistake. This small change to our input causes it to think that this picture of a pig is actually an airplane, which would make me pretty nervous if that was in a self-driving car identifying stop signs. The theoretical guarantees around stability to small changes in our input mean that for wavelet-based neural networks like the scattering transform, this kind of mistake can't happen. So my research is focused on extensions of the scattering transform to textures. Textures are repeating patterns, think like tree bark or the pattern in the carpet. And we usually model them using correlations between features instead of the raw features themselves. Now, moving from raw features to pairs of features greatly increases the number of outputs that we have to keep track of. And it can be hard to reliably estimate all of them from a small sample size. So we proposed including different kinds of correlations in the model to reduce the number of features to a manageable level. So here we have a synthetic image generated using our proposed model. It took only about 1,500 features, where state-of-the-art models use several 100,000 features. So the goal of our project is to learn fewer and more meaningful features in a mathematically rigorous framework so that we can actually explain what these models are doing and offer some guarantees about when they will or will not fail. Thank you.